introduce yourself to the students.
Okay. So hello.
And I will jump in the middle and interrupt you if there's a question in the chat that we think you can answer real quick.
Okay.
Do you want a 10-minute warning when we're getting towards the end?
That would be great. Yeah, give me a 10-minute warning. So, okay. Hi, I'm Anthea Koster, and I'm actually this is a photograph of where I work at the Haystack Observatory in Massachusetts. Right now, I'm actually in Alaska, so it's very early in the morning. And but in the distance here, you can see a very large antenna, and that's actually part of our incoherent scatter radar. So I'll be talking about that in the next talk. But this one is really structured about the ionosphere. And as I was putting these talks together, I'm realizing I'm really kind of throwing a whole bunch of stuff into one lecture. So I tried to keep it to the point, but if there's questions, just ask. So now I have to see if I can move it. What am I doing? Oh, here. Yeah. All right. So sorry, go back. I provide here a bunch of references. If you want to learn more, you can go see these books. Some of them are old, but I would say these are probably some of the best sort of textbooks to go look up and read if you have more questions about the ionosphere. There. And I think you've been getting an overview all of this time, going from the sun all the way through the heliosphere to the Earth's magnetosphere. And you see this very little blue line right in the center here. That's the ionosphere. So in perspective, we're a much smaller piece. And to let you know, the Earth's upper atmosphere and most of the solar system is a natural plasma. Plasma is like the fourth state of matter. Universe is filled with plasma. Ultraviolet output from the sun creates a plasma in our upper atmosphere through ionization. And the ionosphere is an ionized region of the Earth. So I have this movie. I don't know if anybody showed it to you, but I still love this movie because it just puts into perspective the size. And I haven't ever seen anything that's quite like it. I hope you can see it. But we're starting at the sun, and there was a CME, and I want you to see what happens. This is what modelers have to do when they are connecting the models from the solar to all the way down to the magnetosphere to the ionosphere. But you'll see the perspective keeps changing as the CME is propagating. And this is the part that always, always amazes me. That's the Earth's magnetosphere reacting. And again, as I'm saying, the ionosphere is much, much closer to the Earth. So that was just to provide a perspective. And I'm going to now ask, and you can answer this in the chat or attempt it. One, what is the ionosphere? Where is it? And why on earth do we care? And it's really the last question I'm asking. Why do you think we care about it? Does anybody have any answers? And I'll see if I can read any chat things. You may be too. No answers here?
It usually takes a minute for people to type in. So there's usually there's
one. That's a great answer. Yep. Okay. So I think what people are saying is GPS signal, any kind of satellite propagation. And in fact, that's why the ionosphere was first discovered when people started working with radio, because it is an ionized region and there's a magnetic field, electromagnetic wave propagates through the ionosphere. It's a dispersive, well, we'll discuss it, but that's exactly what happens. The ionosphere influences the propagation of radio waves through it, and that's how it was discovered. That's why you care about it, because space weather, or a lot of space weather, happens in this region. and what we can do about it and how we can predict it, that's important. So just remember that, because a lot of people don't understand that it is actually really important, especially for all of those satellite signals that are propagating through. And it is, that's true. It's a transition layer between the lower atmosphere. These are all very, very good answers. And one of the things I do as a scientist is really look at how energy propagates from the solar wind to the magnetosphere into the ionosphere. And then nowadays, we're spending a lot of time looking at how you can see signals propagating from below up into the ionosphere and what we can see. So those are great answers, everyone. Let's see, go down here. So just to give you some, again, general structure, I think I've got a couple of slides like this, but the ionosphere typically starts at around 80, even during the day, sometimes 60 kilometers. That's what's called the D region. Now, the D region does not last through the night because it's a very collisional region. So D region is only there during the day, but we do look at it. Typically where it starts is about 90 kilometers on up to about 120, 130, and that's what we call the E region. Above that, we have the F region, which starts at, say, 180, and it goes on up. And for most of the models, they stop at 1,000 kilometers, but really the ionosphere just sort of merges into what we would say is the plasmasphere. And so when I'm actually tracking or measuring how much total electron content I can see with GPS, I'm actually measuring electrons all the way up to 20,000 kilometers, which is where the GPS satellites are, all the way down to the ground. So just remember that the old original models would stop at about 1,000 kilometers, but it sort of feeds into the plasmasphere, and that whole region is ionized. But the majority or the major region of ionization is what's called the F region. And now one of the reasons, and we're going to talk about this too, that we have different regions in the ionosphere is because we have different constituents at different altitudes. And you'll see that below 200 is primarily oxygen ion, then we have nitrogen or NO plus. Above about 400, it's O plus primarily, and then above that, in the top side, it's primarily hydrogen. So different constituents are the ionization of different constituents, and all the ionization comes from the sun's radiation. They're important, and that's why we have the different, the formation of the different regions. So again, as you can see here, we have the D layer, E layer, F layer, and you can see here's an AM radio transmitter, and it's just showing you some of the propagation that you're going to see, propagation effects. And we're going to talk about that later. This is just an introduction. And this bottom graph right here, I think that gives you, again, a good sense. This is it's the difference between day and night. And I can tell you right now, I'm in Alaska and there's not a lot of night here. But typically what happens, even though the sun's radiation goes away, the F region stays. And that's partly, you'll see this part. The F layers combine from F1 and F2 into one layer at night. The E layer mainly disappears, but it's still somewhat there. And the D layer goes away completely at night. So the different regions are different depending on what's happening. But one reason it's important, I mean, if you're ever, at least in the old days when you had a car radio and you're driving like I did across Texas, you could sometimes pick up radio stations from Chicago. And that was a phenomena that during the nighttime, basically the ionosphere goes away, except for the F layer, which is higher up. So radio waves actually scatter off a higher region at night, and you can actually hear Chicago radio stations, or you used to when you had radios in your car. You could hear them at night. So as I mentioned before, the ionosphere was discovered when people started experimenting and playing around with radio waves. So back in 1902, somebody named Oliver Heaviside, he was in England, he predicted that there was a layer of ionized gas between 90 and 150 kilometers. This was based on research with radios. 1924, Edward Appleton actually measured the ionospheric reflecting layer height with a transmitter going from Bournemouth in Cambridge, and he used a frequency change method to measure this. And then in 1925, somebody named Brett and Tube, and I only just learned they worked actually outside of Washington, D.C. I never knew they were U.S., but they started using a pulse sounding technique and realized that the ionosphere had seasonal and diurnal variation. And in 1926, Robert Watson Watt introduced the name ionosphere. So that's sort of the brief history. And again, this just shows you some of the radio wave propagation effects that we really care about. But you have in the ionosphere electromagnetic wave that's propagating through it. It's a plasma, and it's embedded in a magnetic field. And that is why it's important. If you look at how we describe waves, they're radio waves. We need to look at what? Okay, amplitude, polarization, and wavelength, phase and direction of propagation. They propagate at the speed of light, but actually they don't. We're going to show you that. They're kind of, the index of refraction actually changes it, and they're not propagating at the speed of light. And they can, typically you can mainly superimpose waves, but. So as I just mentioned, the index of refraction is not equal to 1. And this top equation right here, which is n squared equal to approximately 1 minus this omega p over omega squared, the bottom number, omega squared, is the angular frequency of the wave that you're trying to propagate. The top number is what's called the plasma frequency, omega p, and it's defined over here by electron density just times a bunch of constants, right? But this electron density it changes, as you know, as a function of altitude, and it's this property that if we're actually propagating at a frequency that is equal to the plasma frequency, you'll see that n squared equals 1 minus 1, or n squared equals 0. When that happens, the wave reflects. So if you look at it, you can see that some waves in the ionosphere reflect, and it says this happens because it's below the critical frequency. That means it's below the plasma frequency. And typically, that number, well, one, it changes as a function of altitude because the electron density is changing. And it's typically between 3 megahertz and 15 or 20 megahertz. So it's the lower frequencies that reflect. Above that, depending how much they actually propagate through the ionosphere, but they can be bent. And indeed, that is what happens a little bit to the GPS signals. And if you're significantly above the critical frequency, and I would say S-band, which is one of the main transmissions they use for communication with satellite, at S-band frequencies, they're not significantly affected because they're that much higher than what this plasma frequency is. The other thing I'm going to say is that this is a simplification. This n squared equals 1 minus omega p plasma frequency squared over the angular frequency squared. Typically, we write it out, and I think I have that here, but if not, you'll see it in the next talk. The full index of refraction has many other terms, but to first order, the other terms include the magnetic field and the electron collision rates. in most cases, we can actually simplify it to this expression here, but it is a little bit more complicated. That what you're seeing and what I've given here is a simplification. So again, this talks a little bit about what happens when we have a magnetic field in a plasma. And as I said, in the ionosphere, we have the Earth's magnetic field and we've got a plasma. So what you've got is charged particles are gyrating around the B field, and they drift perpendicular when it's due to applied forces. Now, let me just show you this here. Basically, if you're propagating an electromagnetic wave along the magnetic field, the particles or the electrons are going to gyrate. That's called the electron gyro frequency. If it's propagating perpendicular, they're going to have to propagate perpendicular via collisions because their particles are sort of tied to the magnetic field. So here, this omega C, that's the gyro frequency, and you can see if you're propagating along B, you actually have, this is the equation for Faraday rotation. So if I had a linear wave, and that's shown down here, a linear wave, and I was propagating it through the ionosphere, as it propagates through, at the end, it's tilted. It's no longer, it's lost its original direction. So you see this phase shift, and that is actually one way we have to measure the electron density in the ionosphere. And many astronomers rely heavily on measuring this Faraday effect. Now, above this plot here, this again is showing you perpendicular propagation. This is neat. This is from the Forte satellite. It's measuring a lightning strike. So at a variety of frequencies, you can see here it goes from 0 to about 50 megahertz. And this is time in seconds. And what you're seeing is that we're actually measuring the return of these higher frequencies much quicker than we are the lower frequencies. And that's because the ionosphere has a bigger effect on the lower frequencies. And as you know, if it's below the critical frequency, they reflect. But you also see that the waves are splitting. So up here at the very top, we're just seeing one single pulse, right? But down here, we've actually got it splitting up into two. And that's what's called the ordinary and extraordinary waves. And so we're actually seeing that as these lower frequencies are propagating through, the magnetic field is really having an influence, and it's splitting into what is known as extraordinary and ordinary mode propagation. And that's just something they're measuring from lightning pulses. So you can see this, it definitely influences our measurements on electro. Okay, this is it's called the Appleton-Hartree equation, but this is the full index of refraction in the ionosphere. And as I said, it's very much more complicated than what I showed you. But the approximation that you make is this: everything in the denominator basically doesn't count, or what you do is this whole part at the bottom cancels out. You're left with x, 1 minus x over 1 minus x. The 1 minus x cancels out. So you're left with 1 minus x. And if you notice, if you go to this x, that's the term that is the plasma frequency over the angular frequency squared. So that's where it comes from. But these other terms are where you're getting, in fact, this plus and minus, that's where you're getting the difference between the ordinary and the extraordinary mode propagation from this term right here, plus and minus. And what does it do? The two things that you really care about is elevation refraction. So if you were actually tracking a satellite and using radar, especially at the lower elevations, you're going to see it higher up, or your measurement is going to look like it's higher up than it truly is. And that's because it's bent, both due to the troposphere and the ionosphere. So there's a bending that happens. And when you actually get the returned signal, it actually looks like the satellite is at a higher position in the sky than it truly is. And you have to account for it when you're doing that measurement, or you'll have the wrong place. Now, this property is how when you hear the word occultation, that's what occultation measurements are. They're measuring this bending angle. And from that, they're able to infer different properties of both the troposphere and the ionosphere. But this is what they bend. So this is done more in space. For me, I really work with ground-based systems, and I don't usually use anything. This effect is more important if you're at elevations below 10 degrees or 5 degrees. And I usually cut off my data. I don't look at things that are too low. So I'm usually setting a boundary of about 7 degrees. So I don't care about elevation refraction, but this range delay I do care about. And in this case, when you're actually measuring, remember I said that the wave is not traveling at the speed of light. It's traveling slower. Now that's actually, sorry, let me go back. It's traveling slower. And so for GPS, what we actually do to measure the ionospheres, we have 2 different frequencies, and we sort of subtract the range, and what's left is the difference in the observed range at one frequency versus the other. And that's because the ionosphere is dispersive. It affects different frequencies differently. The troposphere is non-dispersive, but the ionosphere is dispersive. All right. So I have another question here. In the solar wind plasma and in many parts of the magnetosphere, the ionization degree is 100%. Does anybody know what the maximum ionization degree is in the ionosphere? Just curious. And you can guess. Somebody has guessed 50. Does anybody else want to know? Want to take a guess? Okay, 10%. All right, the answer is, are you ready? You're getting better. It's 1%. Okay, that's in the ionosphere. The maximum amount of ionization is only 1%. Obviously, it's going to increase as you go higher, but it's a very small part that's ionized. It's that small part that counts. So keep that in mind.
There's a quick question that I think you can answer, which is the scale of the ion gyro radius in the ionosphere.
Yeah,
obviously it depends on the ion, but what is it?
I want to say 1.1 megahertz, and I don't know where that comes from, but I think 1.1 megahertz is an answer to that. But that may be for the electron.
To the gyro radii size.
Yeah. Yeah. What's the size? Well, so it's different.
Size of the gyro, yeah.
It's different for electrons and ions. The electrons are much tighter. They're small and little and more lightweight. So, trying to remember, typically ions are about 2,000 times bigger than the electrons. I think that's a number. So there's a huge difference, and I just don't have those numbers off the top. You can probably go back to that equation that I have there and calculate it. Just realize that we care much more about what the electrons are doing than the ions, because the ions are bigger and slower, and their ion gyro radii is much, much larger. All right, and
then the other, sorry.
Go ahead.
I was going to say, there's another question, which I'm guessing you're going to get to later, which is what's the physical mechanism for replenishing the light ions, protons and alphas in the ionosphere when they are stripped away due to space weather events. But my guess is you might get to that later. Well,
maybe, but how about we?
Maybe.
Well, can you re-ask that question?
Yes.
Towards the end, and we can talk about it, because I may.
Yeah. Well, we also have office hours later, so
hopefully you can
I'll be there for those. Answer that. Okay, great.
Okay. So, what is the ion? So, next things I'm going to kind of talk about: what's the ionosphere made of? What are scale heights? That's very important. Why are there different regions, the D, E, and F? And what's the importance of different processes in these different regions? And how does it form? What are the primary mechanisms of production and loss? And I'm hoping that I've attacked all of these questions in the next part that's going to come, but this is the part I'm going to be honest with you. I'm a little worried that I skipped over things here to make it. But first, distinct regions in the ionosphere form because the solar spectrum deposits its energy at various heights depending on the absorption characteristics of the atmosphere. Okay, and the absorption characteristics depend on what is a primary molecule you have at the different heights. The physics of recombination depends on the atmospheric density, which changes as a function of height. Obviously, there's a less density at the higher we go. And the third point here is the composition of the atmosphere changes with height. And this is just, all of the ionosphere is formed, or things are ionized because they're photoionized by the sun. And one of the things you can think about is that there is a lot more ionization in the equatorial region than there is here, where I am in Alaska. And that's just because of the angle of the sun hitting the atmosphere. But we'll come back to that. It's not quite as simple as that, but that's the main thing. So scale height, that's a very, very important term for what's going on in the atmosphere. But a scale height is a term used to, here I can't even read my thing, used for how a quantity, in this case, our atmosphere, the composition of the atmosphere changes by a factor of E, and it's usually denoted by the capital letter H. Oh, sorry, for planetary atmospheres, it's the vertical distance upwards over which the pressure of the atmosphere decreases by a factor of E. The scale height remains constant for a particular temperature and can be calculated by H equal, this is Boltzmann's constant times temperature, mean molecular mass times the gravity. All right. Now, what happens in the atmosphere, and this is just to give you a sense of what's going on, is that there's a scale height for each one of these different compositions. And because of gravity, that's why we have, at different layers, have different amounts. Like, as you can see, at 100 kilometers, which is the beginning of the ionosphere, we have some N2, we have some oxygen, we have a little bit of helium, a little bit of O2, and some, what is this? N2, and then I can't even see this. This is the oxygen. So these are the different constituents as we're going up. At heights over 100 kilometer, molecular diffusion means that each molecular atomic species has its own scale height. The dominant constituent from 0 to 200 kilometers is nitrogen. From 200 to 1,000 kilometers is oxygen. From 1,000 to 250, 2,500, it's helium, and above that, it's hydrogen. Now, the other thing we have to think about is hydrostatic equilibrium. And basically, you've got the force of gravity on a parcel of air, and it's balanced by the pressure gradient. So if you assume that the temperature is independent of height and, height and, what is that? I can't even see this. Sorry, I can't even, and well, anyway, basically you can attain this following equation for the density, right, of each species, where we have this H is the scale height of each independent species. So the density of the atmosphere falls off exponentially. When we're actually writing it, we have a bunch of these equations which sort of describes what's going on and how you basically generate an ionospheric density profile. But you've got photochemical equilibrium, so you are assuming, and this isn't always true, that transport is not important. So you can write that the electron density is a function of the loss minus the production. So production minus loss, and you're saying it's zero. If the loss is due to electron ion collisions, and that's normally what's happening, we get a Chapman layer. And that can be defined by here, where you have the electron density is the production over alpha 1/2, right? There's vertical transport, and that means sometimes we have it. You can write this equation right here. And treating the pressure forces of the electrons and ions and assuming neutrals are stationary, we obtain this following equation. And if you look at this equation, this term right here, it's the ambipolar diffusion coefficient. And that means that what is actually happening is the ions are the electrons are tied to the ions. And so everything is moving the electrons and ions are moving together. If you look at it in a large sense, and that's sort of the definition of how they diffuse up and down the magnetic field lines. And again, this HP that you have here, that's the plasma scale height. So remember that. And then we have vertical transport velocity becoming this equation down here. And if you put all of this in, you can actually generate the ionospheric density profiles that we have in the ionosphere. So again, for historical reasons, the ionospheric layers are called D, E, and F. D layer is produced by X-ray photons and cosmic rays. It actually goes away completely at night. The E layer, which is near 110 kilometers, it's produced by ultraviolet and solar X-rays. The F1 layer is produced by EUV, and the F2 layer, in that layer, although it's produced by EUV, transport is important, and that's why this layer stays around at night, because of the winds and everything, you still have a number of electrons that are there, even when there's no solar illumination. I mean, I guess if the sun went totally away, you wouldn't have it, but that's not the case. And I guess this is just another one talking about the different constituents in the different regions and the chemistry. And again, the important point that I want to make here are this is the electron densities we're talking about. So D region is much, much smaller than the E region. And again, the majority of electrons we see in the F region, and there they can be up to 10 to the 12th meters cubed, column measurement. The ionosphere has great variability, and that's what sort of one of the things that I study. We have solar cycle variation. So right now, as everyone knows, the solar cycle is picking up. We have larger ionospheric effects. We have day-night variation, and I think I've mentioned that the D region typically goes away, and so does the F and E region, but the F2 region sticks around. And space weather effects, like if you have and I think I have some examples here, but if you have a solar flare, we can measure it. If you have a geomagnetic storm that interacts, we have huge heating effects, and the ionosphere really changes. So these are the things that we look at and study. And for the last thing, I'd like to say a few words about conductivities. And this is actually one of my favorite quotes, and one of the reasons I get excited about the ionosphere. It came from Mike Kelly, who is no longer with us, but in his book, he talks about this equation right here, which you see is basically the winds, the conductivity, and we see here, this is the electric field, and here is the winds and the magnetic field. But basically, this equation basically provides us with the resulting electric field that is as rich and complex as the driving wind field and the conductivity pattern that produces it. So I'm going to talk a little bit about conductivities and how they're important in understanding how the plasma moves. So again, we have the equations of motion, both parallel to the magnetic field and perpendicular. And one of the things you'll see is parallel. We're looking at the collision frequencies. This is for the ions, and this is for the electrons. We're looking at winds and collisions and mass. Perpendicular, one of the things is, as you know, they're gyrating around, but they cannot really move across the magnetic field unless they have a collision. So that's why these collisions are here. All right. And the collision frequencies, electrons and ions collide with neutrals as they gyrate. How they respond to the electric fields depends very much on the collision frequency relative to the gyro frequency. And so here you actually get some sense of what the gyro frequencies are. This is actually an ion gyro frequency. This is an electron gyro frequency up here. Here you have the electron-ion conductivities, and you can see they change dramatically between 100 kilometers and 300 kilometers. So these are the reasons for some of the things we're seeing. We have the different conductivities, the Peterson, which is perpendicular to B. It's given by this top one. We have the Hall conductivity, which is given here, and we have the parallel conductivity, which is given here. And finally, you express all this with the conductivity tensor. And this just shows you, again, as a function of altitude, what the different conductivities are. You'll notice that the parallel conductivity is very, very high, especially as we go up. But in this region below, we have a combination of Peterson and Hall that actually can be quite significant. And I think this is basically just an overall review of what I've just been talking about here. I thought it was a pretty picture, but you can see these are the differences in the temperature between solar minimum and solar maximum. I said the ionosphere changes. This is all of the energy, the different bands coming in and which bands are affecting and causing and generating the different regions. And these are the different constituents in the different regions. Now, I want to end this talking about the differences between the high latitude, the mid latitude, and the low latitude. And I could actually spend a lot more time than I have here to discuss that. But the high latitude ionosphere is extremely interesting. That's where we look at polar cap physics, the cusp that has to do with the magnetosphere and how the energy is coming in, and the auroral oval. So anytime you see an aurora, that's an ionospheric effect. You're going to see that in the high latitudes. The mid latitudes, which is where I live, basically during geomagnetic storms, we have these high latitude electric fields penetrating into the mid latitudes, so they're not as boring as one might think. And I hope that I can show you some very interesting phenomena that we study. But most of us on the planet live in the mid latitudes. And finally, low latitude ionosphere is extremely interesting because that is where the largest values of the electron density exist. It's sort of not actually at the equator, but a little bit north and south of it, and how that develops and what happens. And the scintillation effects are largest in the low latitudes. I'm going to show you this plot, which is not, this basically is showing you, this is total electron content. It's actually a fairly old plot of total electron content from GPS. And what you're seeing is the effects of a large geomagnetic storm. But as I said, one of the things that happens is when we have a large storm, electric fields from the high latitudes actually penetrate into the mid latitudes. So normally the mid latitudes would be this region right in here over the US. And you can see we have something, we call it the storm enhanced density effect that starts here, and we have very intense, in the lower mid latitudes, we have larger values of TEC than we would normally have. At the equator, during this storm, you'll notice there's nothing, or it's much smaller, that the TEC has actually died, or actually it's being transported further south and further north than it normally would be. All right. And these again are just some of the.
Yeah, you have about 10 minutes.
We're about perfect. So here's the plume. You can see this plume. You can see this bulge. You see this, what we would say is an enhanced equatorial anomaly in the TEC. So we're seeing that both north and south. We see this TEC hole that I just talked about. This is what's happening during a storm. Now, I've got a question for you. This is aurora that actually I was doing a GPS experiment in Venati, Alaska. And we would normally expect to see an aurora, I think, in Venati in Alaska. But I want to know, does anybody have any, I want you to see, can you explain these next two photographs? And I want you to answer this in chat. This is aurora seen in Socorro, New Mexico. Why would we see it there? And even further, this was seen in West Texas near El Paso. I'm from Texas, and honestly, I never knew that you could see aurora in Texas, but you can. Now, does anybody have any idea why you can see that? I'm going to attempt waiting to see. No answers? Everybody's quiet?
There's one. Nope, there's one.
Okay, I guess I can't see that. What does it say? Oh, okay.
EEJEIA, related to the South Atlantic anomaly. Supercells form and stretch down to the equator. Very strong storms. There's some local changes,
yep,
storm effects, storms.
Yeah, it is a storm effect. So guys got that right. Basically, the auroral oval expands, and because, especially in our sector, because the Earth, the magnetic field is not a perfect dipole, it's kind of tilted. So we actually can see aurora as far south as El Paso. This was a really big storm, but just recently, March 23rd, 2023, so this March and this April, we saw aurora. I was asleep, but in Massachusetts, they saw aurora because there was a fairly significant storm. And again, in April, it was a fairly significant geomagnetic storm, and they saw aurora in California, Northern California, but still California. So keep your eyes open if you hear that there's a large storm. You're not going to see it unless there's a large storm, but we can see them. And one of the big things during the Carrington event back in 1867, but I could be wrong about that date. They were reading the newspaper by lights of the aurora in New York and even in the Caribbean. So I'm just saying aurora isn't necessarily always observed in Alaska. When we have these big storms, we can see it here. All right, let me go to the next slide. The last few slides, and this is just to have some excitement because I get excited and I want to share some of that. This is actually a storm effect that we measured. This is with differential TEC, and it was a large storm, but notice these like bands that are just propagating. So this is just showing you how some of the energy that's entering in the polar region is propagating down towards the equatorial region. And we believe that these are related to sort of heating effects, large-scale heating effects that are actually causing what's called traveling atmospheric disturbances. And these atmospheric disturbances, which are propagating sort of equatorward, are carrying along the electrons. So what I'm measuring is traveling ionospheric disturbances, but I think in this case, it's really related to sort of the heating and cooling effect that's happening in the auroral region due to the storm. But just the structure to me is just fantastic. Here's something to do where we're measuring solar flare effects. Now, solar flares are really hard for us to predict, that once you see them, the light takes 8 minutes from the sun to reach the earth. And you can have solar flares that last from minutes to up to 3 hours, but they impact the whole daylit side of the Earth, right? The whole daylit side. And this is just, again, with our GPS. Oops, sorry. Go back, sorry. You can see this was, I think here's a movie, which we'll show you. Basically, that turns blue, but see how it turns red? That's the solar flare. The blue part is because we were subtracting off the background, and right before it, we over subtracted. But I want to show you that when it goes red, it even kind of jumps a bit. Notice that jump? That's because the solar flare wasn't like continuing. It sort of jumped itself. And we actually measured that, right? See that here? That's just blue, but here it jumped. That was the solar flare. This is sort of the individual boxes of our TEC measurement. And I'm just showing you that right when the flare hit, a lot of the GPS receivers had trouble because it just happened so fast, they couldn't really adapt. And so in this case, all of these receivers lost lock, several of them down there, and you can see it also happening here. But this is how much TEC actually increased. And you can see this bump. See, it was small and then it jumped up and then it goes down. That's the bump we're seeing in that data. All right. Now, this is another one. This was a solar flare effect, but it was solar radiation effect. So here, the Owens Valley is measuring it, and all of these receivers where they turn red, they lost lock. So at the time we made this measurement, it was made by a Cornell graduate student, Alex Rudy. No one expected that there would be any solar, this is additional noise due to the solar flare. I think I'm calling it wrong, but no one expected that you would see this at L band. And what you can say is what's happening is due to this sort of burst of energy, the whole noise floor in that frequency goes up. So when that noise floor goes up, your signal to noise ratio goes down. So that's what's happening. And when the signal to noise ratio goes down, we lose lock. And so you're going to see, again, as we get into this here, you see all of, it's called a solar radio burst. All of those receivers that turned red lost lock. All right. This recently was the Tonga volcanic eruption, and it induced global TID propagation. But this is from a satellite, and this is just looking down. So this is not ionosphere. I just want to show you what happened. But it's kind of neat. You see this huge explosion, right? As some of that energy propagates up to the ionosphere, and we actually measured it. So you're going to see these waves in this movie, and I want you to see it. So here, energy is propagating from below and coming up. And notice, bang, you can see it. Those, here are the waves following that explosion. And that's the nighttime. But the waves actually lasted and what propagated around the Earth for like 3 or 4 days. It was pretty exciting. All right, so in summary, and I think I've done my timing pretty well, ionospheric science, at least for me, continues to provide us with a wealth of new and exciting observations. And one of the things I'm saying, this, for example, the Steve phenomena, you see this right here, that was only just discovered by amateur astronomers, or I guess Aurora. It's not really Aurora, but they captured it, this. The ionosphere is a major contributor to space weather effects on radio wave propagation and on PNT system positioning, navigation, and timing. We need to be able to predict what's happening. And again, I'm going to leave you with the Kelly statement. The resulting electric field is as rich and complex as the driving wind field and the conductivity pattern that produce it. Okay, so if there are any, am I right on time?
You are right on time. I'm impressed. I think you're the first. Excellent job, Anthea. Yeah, so we'll take any questions. I think you can either put them in the chat or you can just raise your hands. There's a couple of people, Murdy just mentioned that Steve was just in the news again. So yeah, Steve's been a huge excitement, having been a result of citizen science and all that, and all the scientists getting on board and trying to figure out exactly what it is I think that was a very cool thing. And I love that movie of the explosion of the volcano. That's
Oh,
always a
yeah,
cool one
yeah.
to watch over and over.
I
It's kind of
wanted to
crazy.
end on a kind of upbeat.
There you go.
This is really pretty interesting, I think. So
Yeah, that is really cool. Any questions, further questions for Anthea? I don't see any hands raised.
well, I will be here for I have to drive over to the University of Alaska, but I will be here for what's the difference between a TAD and TID? I did go through that very fast. So traveling atmospheric disturbance is basically just the neutrals. Okay, so when the neutrals actually heat up and then they're cooled, that's actually monitored by some completely different system. But we do see those, and we suspect that the TIDs, which is what I can measure, I can only measure electrons, that what's happening is that the neutrals are dragging, in this case, the electrons with them. All right. So TID is traveling ionospheric disturbance. TAD is traveling atmospheric disturbance. And just think of it as the difference between neutrals and ionosphere. Do TIDs, are they, okay, so, and I really did skip over this, but TIDs, we have a large program studying them at Haystack, and there's different types of TIDs. We see them pretty much all of the time. If there's we see them at night, so they're an electric, sort of an electric thing. And what's interesting about the ones we see at night is they're conjugate. You can see them both in both hemispheres a lot of time. We see them if there's a rocket launch. I can see them. I can see them if there's a large storm. I think in the next talk, I'm going to show you some that we see following the eclipse. So we see both large scale TIDs, and the large scale ones are typically related to the storms. And then the medium scale TIDs, those are the ones that are typically related to things that are propagating from below up, if that makes sense. And some of the TIDs, okay, are they always accompanied by, some of them are caused by gravity, not all of them, but some of them. Okay, does the loss of Locke during a solar flare affect all the satellites at the same time? Depends on the receiver and what's going on. I would say that basically the solar flare is going to affect all of the satellites at one time. But when a receiver is tracking a satellite, you can realize that at lower elevation, you're going to have a smaller signal to noise than you are at higher elevation. And so the receiver may be able to track the higher satellites and not the lower ones. But definitely when you have a solar flare, it affects everything on the sunlit part. But the amount of effect will depend what the illumination is, the solar illumination is, and if you're the receiver on the ground, it depends on what angle what the elevation angle is that you're actually having to track the satellite. I hope that's clear in my answer.
Yeah, I think that's great, Anthea. So Nick, now we should probably take a 10-minute break for people to do whatever they need to do.
A 10-minute break would be good.
Okay, and then so we'll come back. Do you want it exactly 10 minutes? Do you want 8 after the hour, or do you want to do a roundup?
Let's do 8 after the hour, just so we don't,
Okay.
Let's
so
keep
8
the
after the
5-minute
top
break
of the
for 10
hour.
minutes, please.
Yeah, exactly. And then since I might be getting into an Uber right around that time, Nick, you want to take over to
I will take over, yes.
Anthea. So when we come back, we'll just have Anthea's second talk, which I'm sure will be just
Great.
as clear as this one. It was great. All right. Thanks, everyone.
All right, stop video.
I'm going to moderate. Oh, thank you. I'm going to moderate this session, so we'll run it the same way. I'll keep an eye on chat, Athena and Anthea, and any questions that I can't obviously answer, I will lateral to you.
Okay, so I hope everybody's listening. So they asked
So
me to.
I'm sorry,
right.
let's get a thumbs up, or you turn on your cameras to give us a sense of who's back. Okay, we're getting some people back, not everybody. More people, okay. Thank you, Eduardo, for waiting. Okay, I think we're ready to begin.
Okay, so we've just talked about what the ionosphere is, and they asked me to give a talk on incoherent scatter radar and GPS, which I have relabeled here to GNSS because GPS is no longer the only game in town. So that GNSS stands for Global Navigation Satellite Systems. And again, this is where I work, and I have this one because these two large antennas that you're seeing right in the foreground, that's the Millstone Hill Incoherent Scatter Radar. But what I want to say is right now I'm here in Alaska teaching at the Incoherent Scatter Radar School, which any of you can apply to next year. And it takes us, we have a whole week to talk about incoherent scatter radar, and that's not enough. So to do this in a half hour is really kind of squishing it. And then I'm also going to be talking about what we're doing with GPS. So I've kind of squished a lot of material here, but we'll go. The way I structured it, we're really going to be talking about two different methods of measuring the ionospheric properties. First is incoherent scatter radars, and I'm going to kind of show you where the radars are that we operate and what they measure. And then I'm going to talk about GNSS and the ground-based network and how it works as a unit and what really it's significant. And finally, I'm going to just briefly introduce you to the Madrigal database, and that's operated by NSF, and it's part of NSF CEDAR, but it's where you can access all the data from the TEC data from GPS and also the simulation data and all of the incoherent scatter radar data. So that's how we're going to do the talk. And again, we're going to go back to radars, because with incoherent scatter radar, one of the things we're using is very, very large radars. And I'm going to try to explain why you need that. But radar stands for radio detection and ranging. Typically, you have a radar on the ground and you send out a signal. It propagates to a target. Normally, we're just looking at a target, and that target then propagates information back. And the return signal goes as r to the -4, right? So that's the range 1 over the range to the 4th. So the further are you away, the weaker your signal. And remember, everything is signal to noise. Now, with incoherent scatter, we're not actually reflecting off a single target. We're reflecting off a volume. And that volume is filled with electrons. And those electrons are dancing around the ions in that group. And so it's a much harder measurement to make. And just to give you an idea, we send out a very high power pulse. It reflects off the electrons, which are kind of being controlled by the ion motion. And then we receive it with a very sensitive receiver. And I forget how many zeros are here, but only that's very, very small fraction of the transmitted power is returned. So that reason right there is why you need such a large radar to actually measure this. And this is just, I'm showing you this to show you a typical incoherent scatter data plot. This is electron density. It's a function of altitude. I think this was actually made at Millstone. And this is hours. So this is a function of time. And what you can actually see and why incoherent scatter is so great is actually you can measure the electron density as a function of altitude all the way up to 800. And you can see how it changes as a function of time. And obviously, it's starting to decay. Remember, I said the E region goes away at night. So this F layer, you can see there, it actually goes up, and we have less electron density at night than we do here earlier on. And then it kind of goes to a much smaller value later on. This is what you're going to get from incoherent scatter radar. And now the capabilities that you can get, you can get this electron density as a function of altitude. You can also get electron temperature, ion temperature. You can get some information about the ion composition and the line of sight velocity. So from all that, you can derive from your incoherent scatter measurement neutral winds, neutral temperature, and vector velocity. And then even more limited, you can get some sense of what the ion neutral collisions are in the E region. You can get some sense of what the magnetic field is that's at the equator. And you can actually regularize and bin and grid the data so that modelers can have an easier time to use it. Now over here, and this is really what takes a lot of time to explain, but when you actually scatter off this volume of electrons and you receive the data back, and if you were to look at it in frequency, you would see that the energy that you receive is sort of spread in two different bands. The big band here, which we call the ion line, that's really, initially, that is where most of the information that we've always used has got. And actually, forget which one, but I think the width of this has something to do. We have to fit this ion line to models. But from here, we get information about the temperature, the ratio of the electron temperature over ion. All of the energy underneath here is equivalent to the electron density. And basically, we can get information from how these two peaks are spread. But this is what we teach you about in the course. You also get now, and this is a new kind of ability that we've had with the radars, to actually look at that what we call plasma lines. This is energy that's coming back, that's Doppler shifted on either, well, it's shifted on either side of your return pulse by the plasma frequency. And from that, you can get a very, very accurate, much more accurate than this ion line technique, very accurate method of electron density. But so I'm just saying it's a little bit more complicated than I have expressed it here, but you get a lot of information from here, the ionic acoustic dispersion equation, you get the velocity distribution functions, and you get this ion line spectra, which I said how these peaks are basically gives you some information of what the TE over TI is. And as I say, I suggest taking this ISR Summer School course. It's sponsored by NSF, and we have a group of 25 students here this summer from all over the US. So definitely consider it. So
we've got two questions in the chat.
Okay, what are the?
So one I think is more general. Why so question about why such a small fraction of the signal gets reflected, and shouldn't the reflectance of the ionosphere depend on the frequency?
Well, the answer is we're reflecting off individual electrons, and that I don't think the cross-section of electron depends on the frequency, but how the energy actually comes back. And if you were looking at the width of the ion spectra, that does depend on frequency. Typically, incoherent scatter radars go from 50 megahertz up to, I think, 1200 megahertz. All right. So between HF to L-band frequencies are what we use for incoherent scatter. Why is there such a small fraction? Well, if you actually do the math, which means you look at what the scattering cross-section is for the electron, the individual electrons, and then you actually multiply it by what you think the average number in the volume size that you're scattering off of is. And remember, there's that R to the fourth, right? Any energy that you're sending out and then it's reflecting back, it has to do with the cross-section of the individual electrons, but you're dividing everything by R to the fourth. And so when you do that, it becomes, that number is, when you work it out, that's what it is. And that's why you should take the incoherent scatter radar, because we spent a lot more time on that than I just did.
And by R, you mean just the throw distance of
the range from where your radar is to where,
which is,
say we're trying to scatter off 100 kilometers.
Yeah, right.
So 100 kilometers is the range. And it's R to the fourth, but it's kind of tricky with incoherent scatter. You're actually, that R to the fourth may become somewhat R to the second. I'd have to really show you the equations, and I'm more than willing to do that if you want. I'll give you a plot in the, because I didn't go into that detail, but I can certainly show you that equation in our hours.
And somebody's put it in chat already. So another question just came in was, are there other types of radar other than incoherent scatter radar used for ionospheric studies?
Yes, but yes. We're working with meteor radars right now. I would even say ionosons are not really radars, but sort of they are. There's many other radars that are used, but incoherent scatter are the ones that get you the most detail. And I think people don't realize how important they are for calibrating satellite missions, for actually getting these parameters as a function of altitude. No other instrument can do that. You can get electron density, or you can get this, but you can't get everything. ISRs are unique in that. So I just want you to, I'm going to go through some of the ones we have here in the US, but I want you to think in terms of space weather effects, because we're not using the ISRs to measure space weather effects, but in many cases, we have the availability of real-time data is either currently available now or it will be in the future. We have, at Millstone, we have over 50 years, and it's available online, of historical data. But one thing we're not doing right now is working as a coordinated sensor network. So the Millstone radar is not really tied to the ones at Pfizer and Heliophysics, but I think we could work much more as a coordinated network. But this is a space weather effect that were measured at Millstone some time ago. But again, you can see we were looking straight up, and this is electron density is a function of altitude versus time. And you see this huge hole that's coming through. That was, again, this is a storm effect, but these large gradients, these are the gradients that cause trouble for navigation. This is the type of thing that we can measure, and we can measure it in huge detail. And it's from that detail that we can sort of understand what's happening and what's the physics behind here. Next slide. So there's really been a global network of incoherent scatter radars. Right now, I guess everybody knows Arecibo no longer works. My advisor, I actually got my PhD at Arecibo, so I'm still quite sad about this. Sanderstorm was also closed, but we still have a radar here at Poker Flat in Alaska. That's why I'm here teaching the course. We have one in Resolute Bay, the north and south face, and we have one in Heliophysics in Peru. These are the ones that NSF operates. Now, there are other ones around the world, and some of them, like Altair, is not, it's occasionally used for incoherent scatter. It's run by the Air Force, but this all of the data is available in the medical database, and I'll show you that. But again, I want to just say that ISRs can measure physical properties of the space environment as a function of altitude. They can measure electron density, electron temperature, ion temperature, plasma velocity. They can infer electric field strength, conductivity, current, neutral, air temperature, wind speed. And they can do this as a function of altitude. I don't know of any, well, I know there's no other instrument that can do that. But the limitation is you only get it around the millstone site. You only get it around the poker flat site. I mean, it's not a global view. It's a very, very, it's like at that pinpoint, you get all of the information. But if you want to make a global map, you're going to have to combine it with other sources of data. So this is Pfizer. This again is where I am right now. It's a high latitude radar. And they can do these integrated real, I think I actually, there should have been one more. I wonder if it got canceled. There's a similar radar riser, which is the one that's in the, which isn't here. So I don't know what I did with that graph, but it's another face just like this, and it's in the polar cap. So it's trying to make those measurements. Pfizer is here right outside Fairbanks, and I would say it's a high latitude radar. So I've actually looked at it, looking at the electron density. I think I've got that here on one of the later plots showing you the increases in electron density when there's aurora. But that's what they use it for. In fact, I was here for a rocket campaign a few years ago, monitoring auroral features, and they have this real-time display at the Poker Flat rocket range using the ISR data, so that scientists, right before they are tracking, right before they launch a rocket, they can see here, this is a display of the all-sky cameras, but this is actually information about what Pfizer is measuring in terms of electron density at any given time. So one huge advantage is that Pfizer now operates continuously. It's always on. And that means you don't have to plan. I mean, if there's space weather events, you're going to measure it. And that's, for example, they did it. They were just on for an IPY mode during the 2015 St. Patrick's Day storm, and they were able to monitor it as it happened. So one of the huge advantages you have of operating continuously is that you can capture things that you weren't even planning to capture. And they're able to do it because it's a solid state array, and it's actually much cheaper to run continuously than, say, at Millstone, where we have a steerable dish. This is our radar, and as you can see, there's two antennas. This antenna here is a zenith antenna. It looks straight up. You can't really move, but it gets you the zenith profile. And then we have the steerable dish. So when we're operating, we actually switch back between the two antennas. We do a zenith, and then we send a pulse out to the steerable, and then we go back to zenith. So at any one time, we're getting two measurements, and this dish actually can steer both in azimuth and in elevation. So we actually can see, because of this steering ability, we can see all the way into Florida and fairly far north, just by being able to steer in all directions. And here, in fact, you can see we were steering, and this actually, when we say SED region, that's really one of the space weather events. So this is all mid-latitude. This is electron density, and as they're going up, you see there's a trough region, and now we're going into the high latitudes, and it's much more patchy, which is what we would expect. We operate now about 1,000 hours a year. Right now, we're doing an upgrade, so the dish is not working. And we work with a lot of satellite programs in calibration. For example, we worked closely with Van Allen probes and MMS.
Anthea, a couple of questions in chat. I think they're both related, which is, you're seeing both vertical variability, but also horizontal variability.
Well, our measurements are always going to be line of sight, but we do see some horizontal. If you combine the line, if you're looking in one direction and you're looking straight up, you can get some information about the horizontal. Does that make sense? You're not measuring horizontal because it's a line of sight measurement, but you can infer horizontal information. Yes.
Okay, great. I think that covers both of those questions. So, yep.
We can also, as I said, if we needed to, we can operate a 2 to 3 minute delay behind real time. That's not being done right now. I mean, when we do operate, we do it 2 to 3 minute of delay. So we have a real time mode when we're in operation. And all of the data goes directly into the Madrigal database, which I'm going to at least mention here. And there's observations are available right away. So there's a lot of, I would say, advantages to what we have set up. Next slide. Now there's the last one that NSF is at least involved with is the Heliophysics radar in Peru. It's a 50 megahertz radar. And because of its location, it actually propagates directly perpendicular to the magnetic field. So the kind of ISR measurements it makes are very different than the other two radars just because of the propagation mode. But they've done a lot of very, very interesting things because one of the things they measure is this effect at the bottom, which is called spread F. That's when you have these large plasma patches that form. Associated with those patches are electron density irregularities, which cause scintillation. And they're now developing this ability to try and forecast or predict when they're going to see these kind of spread F type features in the data. So they're trying to monitor this and trying to work with other people to try and predict when this will happen. And you need to know when this will happen because this is associated with when they're going to measure scintillation. Scintillation in the equatorial region typically happens post-sunset. But it is the largest scintillation that you're going to have. And nowadays, just to give you an example, people in Brazil use GPS to do precision farming. And one of the biggest problems they have is that they actually want to use GPS 24 hours a day. And you can't use it when you have these huge scintillation events. And as I said, they're not every night, but when they do happen, they're very intense. So they're trying to predict that. And that's the type of research that's going on right now at Heliophysics. So in summary, and as I know this is just a flavor of what I've given you, I think Incoherent, I just want to show you, they're really able to provide you detailed looks into ionospheric properties and dynamics. And they're the most detailed looks you're going to get. This is from Pfizer. Again, this is just going from 95 to 120, but I believe Josh Semeter published this. This is an aurora, the effect of the aurora coming in, so you can see at different altitudes what's happening as the precipitation comes in, and it really affects the lower altitudes. This is Arecibo data, but you can see all of this structure, the topside layer, that's all real, everything that we're seeing here. And I think actually you're seeing kind of a TED kind of effect, but that's why, yeah, incoherent scatter really, really helps us understand what it is we're seeing. Now, from that, we're going to move over to GPS or GNSS, which is more, even though my PhD was at Arecibo and was with Bill Gordon, the the discoverer of incoherent scatter, I ended up spending most of my career on GPS. different sensor, different ability to actually measure the ionosphere. And the only thing GPS measures is the total electron content. So we don't get those altitude profiles. We just get one value. It's the TEC, it's integrated, and it's all the way from the ground, all the way up to the satellite. So up to 20,000. And the units, the TEC units is measured in 10 to the 16th electrons per meter squared. So just keep that in mind. Now, again, we're talking about radio waves that could propagate through the atmosphere and the ionosphere. And when they designed GPS, they knew that these two regions were some of the largest error sources that they would have in their positioning and navigation solutions and timing. And because the ionosphere was dispersive, and in fact, the ionosphere is the largest, or can be the largest error source in navigation. So you want to remove it. And they knew they could remove it if they made GPS dual frequency. And that's why they did it. They wanted to be able to take out the ionospheric effect and not to have to worry about it. You have to predict the troposphere, but that's actually, to first degree, it's fairly easy to predict the troposphere. But the ionosphere, you can actually measure the effect if you have the two frequencies. So just to give you a bit of a background on GPS, they can have at most, they cannot have more based on their current signal structure, 32 satellites. And right now there's 31 that are operational. They're in 6 orbital planes. Those orbital planes are at 55 degrees elevation. And I just want to say that because actually it's 53 degrees elevation. GLONASS, which is the Russian system, is much higher. It's, I think, 63 degrees inclination. So combining the different systems, GLONASS and now the Beidou, we really get much more information. And that's why we don't want to just say GPS anymore. There's 4 to 6 satellites per plane, but it's really, you only need 24 to be operational. Right now, there's 31 operational satellites. And they're at 20,000 approximately in 12 hours round trip. That's all you need to know there. The way they work is that each satellite has a very accurate clock. They actually monitor these clocks and from Colorado Springs, and they send up corrections to the clock, and those corrections are actually transmitted to each receiver. So they're saying, here's my clock, here's the corrections you have to apply to it, and by the way, this is my position. Once you have that and you transmit the signals on 2 frequencies, you can actually then back out where you are on the ground. The first satellites were launched, I can't read this, in 1978, but when I started working with them in 1986, there were only 4 visible at any one time. And now, as I said, there's 31 in orbit. All right, but the way, again, it works, the positioning and timing is that you have to really track 4 satellites at once. But you solve with those 4 satellites, which are sending you their time, they're sending you their position, they're sending you a bunch of other information. With that, you can calculate your position on the ground plus a correction. This B is a correction for your clock. So that's how you get this very precise time as well as your position from GPS. In perfect world, you would do this perfectly, but of course, nothing is perfect. There are errors in the orbits, there's errors in the clocks. They actually deliberately don't send you perfect orbits. That's the military, because they keep those for themselves. The receivers all have a little bit of noise. There's always multipath, and of course, there's the troposphere and ionosphere. So let's go back. Some point. And again, I think I've gone through this. The ionosphere does both refraction, i.e. it bends the wave, and it also is dispersive. It's like a prism. It separates out the different frequencies. So those are, just keep this picture in mind. That's the most important thing that the ionosphere does based on the Appleton-Hartree equation, which we went through earlier. And again, it gives you both elevation, refraction, and range delay. So our measurement, just to give you a sense of how big this is, our measurement is the difference in the range correction between the two frequencies that we're tracking. All right, and that works out. I mean, you can, if you have the range correction at L1 and the range correction at L2, and then you subtract this out, you can actually back out what the TEC is, because you have this you have the measurement at L1 and you have the measurement at L2, you just subtract them and then you back out, you use these constants and you can get the TEC. So to give you an idea of how large these range corrections are for GPS, if you had 50 TEC units just vertical, that's actually quite a lot. For L-band, you could have up to 12 meters of correction. So I would say normally at a haystack, we would have maybe 20. So it's much smaller, but certainly in the equatorial region, you can have as much as 100 TEC, and you can see by then you're talking about 26 meters. Remember, when you want to land those planes, you want to have your measurement better than 5 meters. In fact, you really want to have it more like 3 or 4 meters. So this is a large number. You have to take it out. Again, our measurement is here. It's the difference between the pseudo range measurement at 2 frequencies. Everything else cancels out, and that's how you work out what the TEC is. I'm just keeping this in for you so you have it to look back at. This is just an illustration of what a single satellite track would look like. There's both the group delay and the phase data. The phase is actually much smoother than the group delay. The other is fairly noisy. That's why we always combine the two types of data to get the smoothness of the carrier phase, but the absolute value of the group delay. So when I first started doing GPS, everybody was telling me, oh, it's useless. I'm really, the big scientists in the field were saying, you're never going to get anything that's useful out of GPS. It's just TEC. You can get it, from different directions, but so what? But right at the time when GPS was coming online, that is when the internet started. And that's when data started sharing. And of course, they built up a huge network because they were trying to monitor earthquakes. So the earthquake people, the geodesists, were really big on this, and they actually shared their data. So you can actually get data from all of these sites. This is actually going back to 2003. We download up to more than 6,000 sites a day now to process. But once you have this distributed network of sensors, you can see things that we couldn't see before. And just for example, it was when we first did this is when we first started being able to see this, what we call storm enhanced density effect. Nobody had ever really, we knew it happened because we saw it just over Millstone, but nobody had ever seen it over the whole globe like this. And this was phenomenal. Once this happened, you were going, oh, we can tie this with our measurements from incoherent scatter and with other measurements. And all of a sudden, we have a global picture of what the changes are in the ionosphere. And it was a major effect. But I just want to say, when I first started doing this, there were so many naysayers. So just remember that. Don't listen to them. So now when we're processing data, and this is, I guess, the next steps, not only do we process data from ground-based stations, and each ground-based system now tracks multiple satellites. It's not just GPS. You can track easily. If you have a good receiver, you can see 50, 60 satellites at one go. But you can also track things from satellites in space. And by doing that, you can really combine the data and start to get the profile information that we haven't had before. So I think that's the next step, is really taking advantage of everything that we have available. But we don't get temperature information. We just get electron density and electron profiles. All right. So I have a quiz, and I think I actually said this how many GPS satellites are needed for a fully operational system and how many are in operation now? I think I already told you that. But can you name some of the different constellations? Can anybody name it? And can anybody also just guess how many pairs of signals are available right now among the different constellations? So I would say, can you answer in chat these last two? And let me see if I can see what you're saying. Oh, yep, that's good. Harsha, that's the right answer. You've got all 6 of them. I'm very proud of you. 32. What's 32? 32 is so no, fully operational, you only need 24. And right now we have 31. So Icon Swarm are not GPS satellites. They are, they may have GPS receivers on them. I don't know if they do, but they're completely different. It's GPS, Galileo, GLONASS, Beidou, yes, relativistic corrections are definitely taken into account, and you have to. So I want to know, does anybody want to try guessing how many signals are available? If we were going to try and process it, how much is available now? Does anyone want to guess? Not yet 1,000. The answer is there's over 400. Now, I haven't done that. I have never done that, but I would say we're behind, but we typically can process about 55. But I think that the more signals and the more satellite pairs we have, the better off we're going to be. But okay, so the problem is you can't, when you're saying 31 squared, it's not just GPS. We're now looking at all of the different ones from the different satellites. So it's now about 400, and it's not squared. But anyway, that's what we're talking about. All right, what can we do?
One more quick question on the video you showed. Somebody was asking about, there's a what looks like to be a satellite path that gets that goes through.
Oh, that's TOPEX. That's actually not, that was a TOPEX satellite, and TOPEX does give you a dual frequency measurement, but it actually doesn't work. It's a different frequency, and they're reflecting off the ocean. So it's just another way of getting TEC. I think that's what you're seeing. That was
Okay.
a TOPEX.
Great.
Okay. So ionospheric parameters that you can use GNSS to measure. So again, ground-based receivers can give you TEC. Is an altimeter is, well, you can't, let me say, if you have a dual frequency altimeter, you can compute TEC. All right. It's not, I mean, they're using altimeters to actually, they use dual frequency to take out that correction. We use it as a data product. Okay, but it has to be a dual frequency altimeter. So ground-based receivers are measure TEC, scintillation parameters. So that's the S4 is an amplitude kind of variation, and we use that for the equatorial region, and the sigma phi, which I will show you data. That's something which shows you the fluctuation that you measure in the phase. So those are the two parameters for scintillation that you can measure. Space-based receivers, which use that occultation, and I'm not going to show you too much of that data, but they can measure electron density profiles. And they're now actually, I'd say this is a big area that people are really starting to go into. They can also measure S4 and sigma phi. All right, my next slide. So I want to show you this again. This is, how much time do I have? Oh, I'm doing pretty good here. And maybe early on this one. This is going to show you what happened during the last eclipse. And of course, we are currently trying to get ready for the upcoming eclipses. There's going to be one in October, and there's the big one, which is going up over New England, is going to be in April 2024. So there's one in October this year, and there's going to be a big one in April 2024. But here you're going to see as it goes, this is actually the hole that that was created in the ionosphere following the eclipse. And I'm going to show you this. One of the things you're going to see, and we don't know if this is real or not. Do you see these waves? They're kind of like bow waves that follow the eclipse right over the center. We think that's related to the eclipse. It's a supersonic effect, and think of it like you have a swan on a lake, and the swan is going through, and you have those waves that are coming out after that. We think this is what we're seeing, but it's still not confirmed. We have to actually do this measurement again and see if we see the same thing. So this is one of the things we hope to measure with the upcoming eclipse in April. Okay. This actually is an example. Again, I'm showing you some sort of highlights of GPS results, but here you can see TIDs. These are medium scale TIDs, and you can see the same ones in the air glow emission. This is an older paper that you can see. Here, I'm just going to get on my hobby horse of trying to combine data sets. And this actually was an aurora. We were actually measuring it. This is Venati, Alaska. So this was the one and only time I've ever been in minus 47 degree Fahrenheit temperature. It was cold. It's about 250 kilometers north of Poker Flat. We had GPS receivers both at Venati and at Poker Flat. There's a large rural arc. Pfizer was collecting data, and this data is actually pointed over towards Venati. And what you can see is that right at 10 o'clock, when we had a magnetic substorm start, there was a huge increase in TEC. And what's nice about Pfizer is we can see it actually went, this increase was from like 120 all the way up to over 300. And you can see it actually stays enhanced. There's enhanced plasma they only went operationally till 11:30 that night, but you can see there's this enhancement the whole time. Now, if you look at the TEC data that I measured at the two sites, here at Poker and here it was at Venati, and this was using all of the satellites I had, Venati actually goes up first, and then a little bit later, the Poker Flat goes up. So we see it first in Venati, then in Poker, and I don't know that you can see it as well on this graph as I have data, but it's by combining this type of information that we can really start to understand what we're seeing and why we're seeing it. This actually is from March 23rd. Remember, I said we saw aurora on this time during in New England, but this is actually the TEC, a total NC. It goes from 0 to 50. So you can see all down here, it's at least 50 or higher. And all of these dots here, this is phase scintillation. So right at the end, and I want you to understand that some of the scintillation we're seeing is actually to the storm enhanced density feature. So it's due to the irregularities in these gradients in the TEC. But earlier on, you're going to see the scintillation, and it's due more to, see when it goes all over here, patchy, that's due to the aurora. So we have scintillation from both the aurora, and I've got other plots that I don't think I have here where it's overlaid onto images, but you can see the two different kinds of scintillation, the causes. One, it's from all of the aurora that's coming in, and then you see it right here at the very end. That's aurora. And when you see these structures at the end, that's it. So then now we're going to talk about how do I access data and where is it? So it's in the Madrigal database, which there. that's where you go to get it. It's the Upper Atmospheric Science Database used by groups around the world, but it's supported by the National Science Foundation. We run it at a haystack, but I just want to say this is an NSF-sponsored database for all of CEDAR. And we have data, all of the incoherent scatter data that exists is in there. So if you actually go and are interested in seeing it, just go to Madrigal and pick out the incoherent scatter radar, and you can actually, it produces plots so you can see what we saw for any interesting time period that you want to look at. We actually have a number of different instruments in there. There's 22 data from 22 different incoherent scatter radars, 3 MST radars, 16 MF radars, 7 meteor radars, and that's probably going to increase soon, 23 Fabry-Perot interferometers, 6 Michelson interferometers, 4 LIDARs, 4 photometers, and the GPS data. So I, of course, work primarily with the GPS, so I'm going to tell you a bit about that, but we have this standard product. So these kind of maps are available for any day since 2000 on the web. You can download them, but these are the bin data. So here we provide the data. The maps are 3 degrees by 3 degrees by every 20 minutes, but we also provide the data in HDF5 format, 1 degree by 1 degree bins every 5 minutes. When it's white, where we don't have data, we don't put anything there. We don't try to model. We provide vertical TEC estimates and errors as a function of geographic latitude and longitude. We only provide data where observations are available, and we don't attempt to model it where it's not. And we are using everything that we can. Now, right now, we're processing GLONASS, and in some cases, Beidou, but we're still trying to increase it, and we are getting the Cosmic 2 data in there as well. The line of sight data, which is what we use to actually get the differential TEC product. So at any time we're looking at TIDs, we have to use this. These files are huge, and they provide all of the line of sight data for every receiver that we process. So for each of the 6,000 receivers, for every line of sight measurement, we have it in there. The data is provided every 20 seconds or 30 seconds. We give you the satellite and receiver ID, the latitude and longitude, the pierce point that we use. So if you want to actually change that, you can go back and change it. The AS and L to the satellite, but the one problem is the files are really large. You really can only download one at a time. We get a lot of complaints about that. Oh, why can't we process this and just take what we need? The files are too large for us to do that. So that is the one problem. It takes a while to download them, but they are in the HDF5 format. And you can find everything you need here on the web. There's a whole documentation about how to actually download the data and access it. And furthermore, if you have any questions, you can contact anybody at Millstone and we can help you. So in conclusion, and I don't know if I'm too soon or too fast, but I think that for the future, we really need to find easier ways to integrate the different data types. I want to, again, argue that incoherent scatter data is really important, and as a telescope, I think, for really seeing the individual processes, but you need to combine it with everything else you can get. We need to utilize all data signals that are available, so we need to start processing everything. I think being able to improve visualization of data sets is critical, standardizing data formats. I'm excited about what's happening with the artificial intelligence and machine learning. I think we can really actually go back and look at our data sets and come up with new and exciting ideas. And I hope that we can all work together and cooperate. So as I said, this is hard because these are two very separate topics, and I know I only just touched the surface, but I hope I got you interested, and at least you know to go to Madrigal and how to get the data. So I don't know how, I think I'm doing okay on time, right?
It looks like you're doing just fine on time. If you can take a couple of questions, there's a couple in chat right now. And about specifically about Madrigal. So does Madrigal differential TEC product?
We do not, yeah, that's a good one. We do not provide the differential TEC product. What we give you is the line of sight product. So the way differential works is you have to come with some method to actually subtract off. And I think everybody does that differently. So we give you the tool. I mean, you have the data that you need to produce it, but you would have to do a little bit of work to decide how you want to subtract off the background TEC. And if you were interested in just one particular day or something, you could probably contact us and work with us to get that day analyzed.
Okay,
Python packages, certainly a lot of packages are available. I would say go to the website. I think for certainly to download them, they're available. To plot, I think we provide plots already there, but I think you can talk to us and we can provide you with that. It's not, I don't know if the plotting packages are on the web because it depends on how you want to do it. And you know how Python changes all the time. So, okay, Madrigal differential TEC. So typically, I'll go back to that one. When you're doing the differential TEC, you really, in all cases, when we give you the TEC, we're using a combination of pseudo range and carrier phase. The accuracy, the precision comes from the carrier phase. So we've already done that combination for you. So you're essentially using the carrier phase measurements when you're doing the calculation for differential TEC. All right. Any other questions?
There was one back at the beginning of your talk regarding the electron density below 200 kilometers. And so the question was, why was the electron density small?
Okay, so it can be measured. I'm not sure. I may not have shown you a plot that had it. In the old days at Millstone, we did have trouble. If you look at where we are, the way the radar works, there's the New Hampshire mountains, and they used to scatter back our signals. So until we did this fancy clutter subtraction, which we now do all the time, we had trouble measuring below 200 kilometers. But nowadays we measure, we always measure below, starting at about 100 kilometers. The other thing I can say, though, is at night, you may not have much until there's just the ionosphere decays at night. So it depends on what time of day I was showing you, whether you don't see it because it just wasn't there. But we do measure below 200 kilometers. I should also say, and again, you should take the ISR course, but to do these measurements, we have different waveforms. So if you look at it, we use what's called a long pulse to measure things above. So we have a larger range resolution above 200, and we use a coded pulse, a Barker code below 200 kilometers. So some of the things that you may be seeing is that we're only showing you the long pulse data, and you have to actually merge it in with the coded pulse to actually see it. I hope that's clear. So to actually make the measurement, we are using different pulses to actually get what you want. And you would learn more about that kind of signal processing if you took the ISR course.
And I know you said you had to go right at the top of the hour. There's a few other questions in the chat, and people could I'm sure we could continue for a while. Do you want to put those off, or?
Well, let me do one or two more, and then I'd say let's meet me back when I transfer over to University of Alaska. Let's see. The first one I said, yeah. Can you spit ionosphere coal that happens during aurora? The hole in the process that I'm not sure about the hole during aurora. Well, typically what you see during aurora is actually not a hole, but you see we measure the precipitation. So aurora is usually associated with electron precipitation coming in from the magnetosphere, and that actually increases the TEC, not a lot, but you can frequently see it when we're actually measuring the TEC during time periods of aurora. There'll be a slight, you can see an increase of TEC, and that will stay because it's nighttime, it doesn't decay. It'll stay for an extended period of time. But if you're talking about what happened when we had those large gradients, the SED, then that's kind of another story. And then you have really strong electric fields. So on one side, you're going to have these really sharp gradients that are related to electric fields that are being established during these storm periods. So, and then when you're saying, again, there's then an ionospheric hole that happens at the equator. And that's a whole different process. That's due to what's called penetration electric fields that are imposed by the ionosphere, by the magnetosphere, and they happen during these large storms. It's much more complicated than I can probably address in a few short sentences, what's going on during a large storm. So I don't know that I've done a good job with that question. And then there's a question here about the March 2023 storm. Well, one, that data is, if you go play around on, Madrigal, you can see it. And yes, we do see both phase and amplitude scintillations. The amplitude scintillations are primarily looked at in the mid-latitude and equatorial region, and the phase scintillations are what's important for the high latitudes. So I only showed you phase scintillations because I was looking at high latitudes. But in our database, what we have is, we don't have a lot of measurements right now, but we have some from the Italians actually in mid-latitudes and equatorial regions. And you can see amplitude scintillations during that storm. And that data is on the data. It's in the database. If you email me later, I can send you instructions how to access it.
Okay, great. Why don't you relocate? And let's reconvene at the bottom of the, for those on near the top of the hour now, let's reconvene at the bottom of the hour. And then and for those on the half hour, you'll be at the top of the next hour. Anthea will spend a little bit of time doing general discussion and answering other questions, including the one about impacts on wildlife that we didn't get to.
Impacts on wildlife? Okay, we'll talk about that later.
Yeah, we'll talk about that later. Yeah. And so so Anthea, if you need to go, that's fine. And I'm going to give people some other instructions for the activity later.
Okay.
Today after the meal break. So
thank you so much.
While you're on your meal break, everybody, please go back to the Miro board and start to try and arrange yourselves with like-minded individuals who are posted some ideas. Looks like we have a larger solar group already. Maybe that solar group can start to break up. I've got a second solar panel set up for you, and you can start to break up into two groups perhaps to discuss two different things. And same thing with the, with the solar, wind, and heliosphere group, as people start to join that. If you didn't add your name to the Miro board or any ideas to the Miro board, then please go to it. And even if you're just put your name on a sticky and put it someplace so that you can decide where you're going to go during the after lunch or after meal discussions. And just as a reminder, here is the link in chat to the board, right? So while we're doing that, oh, and looks like, yep, somebody's so. And if you find that you feel like there's another group that I haven't identified that is a separate thing, feel free to copy the template, drag it someplace, and make your new group, right? And I don't move anybody else's stickers. Let them move them so that they know where they are. But certainly communicate with people and invite them too. So, and so we'll be back again in about 20 minutes till Anthea's back on to answer questions, and then 50 minutes when we get started on the activity. Any questions or comments on what we're doing right now? Going once, twice, sold. Shelley, are we still recording? Yeah, I think we are. We can stop the recording.
I'm sorry that. Sorry, I'm here. I can hear you.
Oh, no problem whatsoever. So, if can people give us a thumbs up if they're online, and if we've got questions for Anthea on. Okay, great. So a few thumbs up. If you've got questions, you feel free to put them in chat or just unmute yourself and we could spend 20 minutes talking. So I think one of the questions that was in chat earlier during your lectures was about the harm to wildlife. If there was any harm to wildlife when you were running the incoherent scatter radar, and so I suspect I know the answer to that, but I don't know what the if there's any particular considerations or.
So, well, one, like with the radar, the one at Millstone, we have had some issues with eagles actually nesting on the structure, and we've had to move the eagles. We've never noticed anything, like no dead animals or anything. However, I will say there are some concerns of radiation hazards due to the side lobes. Like when I drive, I have an insulin pump. I'm diabetic, for example. Mm-hmm. And not this version, but 2 versions ago, I typically would lose an insulin pump. It would just die from too much E&M exposure. It happened once a year. Every year I had that model of pump. So I think I can say for me, it was kind of a pain. But in general, the answer is no. No, there's not. I mean, you don't want to get in the near field of a high power radar. That's not a good idea, and we don't allow it. We are concerned about some of the side lobe issues, but there's nothing that we're aware of.
Okay.
But we do take that very seriously. So It's not something that we don't look at and
But you haven't
measure.
had flocks of birds falling out of the sky or something.
No flocks of birds, no, nothing really bizarre other than the eagle nests that we've had to like clear out. So they felt safe enough to nest there. We just didn't think it was good for them.
Right. Probably not good for your return signal either. Yeah. So other than, I mean, of course, there's always disruption when you're putting in an installation any place, especially since you're putting some of these in fairly remote areas, and there's other concerns about land usage and that sort of thing. But
Well, so going forward, that is a big concern. And I would say, I don't know if people are aware, we here at Alaska, they run a facility called HARP. If you want to look up on the internet about really strange people, it's an ionospheric heating facility.
right.
And just type in HARP and aliens, and there's like this huge network of people that are convinced we're trying to control people's minds, or you can't let people go too far down a path, because things get made up that are just ridiculous. But
Right.
These are some issues. We need a better job of science education and making sure people are aware of what we're doing and why we're doing it and what are the advantages, I would say. And at Millstone, we do have, for us, it's more of an issue for the radio astronomers who are mainly just listening, but they really are very concerned about the encroachment of, like, we had one guy go around and look for all the garage door openers in the area because their signals were spilling into his observation. It was called the deuterium array, and he was seeing the signals of the garage door openers. And certainly now frequency spectrum issues have become huge with all of the new satellites that are going up there and what's happening. So this is an area of concern.
Others have questions based on Anthea's talk or any other things regarding the incoherent scatter radar. Hagar.
Yes, hello.
Hi.
Hi, thank you for your protective presentation. Actually, I asked you earlier, do TIDs accompanied by gravity waves or not? And you answered not all of them, just some of them. So my question right now is, how can we detect if TIDs are accompanied by gravity waves or not? I'm just wondering now if we can observe the signature of TIDs. The signature of gravity waves while we are observing the TID. Another question, if there are any specific condition for the correlation of the occurrence between TIDs and the gravity waves or not? Thank you.
So, well, gravity waves typically, so I guess the question is, how are they related to gravity waves? And the ones that we normally consider being related to gravity waves are the medium scale TIDs. So those are the ones like, trying to think, if you had a thunderstorm or a mountain wave or something, that is typically a TID that's propagating up. And if you talk to people in Colorado, one of the things they're saying that as a gravity, it's which gravity waves actually couple with the ionosphere. So not all of gravity waves actually can go up and enter into the ionosphere. Only certain ones can. And it's hard to really, unless you know how these gravity waves are generated, it's hard to be able to separate out what we're seeing and what's the cause. Does that make sense? Like, if I can see I can see a measurement of what it is. And if I know it's a large storm and it's a very large effect, then it's a large scale TID and I know it's a geomagnetic storm. But for example, when I was showing you those waves following the eclipse, one of the competing theories is that there were thunderstorms in that part of the country at the same time. And what we were seeing is an amplification of those TIDs due to those thunderstorms. Now, what we are doing, and I think I showed you some of that when we did those optical images from Japan and compared them to TIDs that were measured over Japan. Those were clearly gravity wave related. All right, those were related. I don't know. I mean, again, I don't know that we see gravity. We see the second or third as the gravity waves couples higher and higher. I don't know whether it's called a gravity wave in the ionosphere. It's that energy from below has actually coupled in. So how you want to describe that interaction, I don't know. How else to answer it? So I guess this is, I think the easiest way to answer it is it's still an ongoing research area, which waves are what, and it's not something that I have all the answers for. I do know that we saw they were called lamb waves following that Tonga explosion, and that we were able to determine that because of the speed they were propagating. They were propagating at 350 meters per second, where some of the other waves were much faster, and I think there were some waves that were slower, but the ones that were at 350 meters per second, they fell into this category of lamb waves. So by looking at the TIDs, you can sort of you can determine which direction they're moving, what their propagation speed is, and their wavelength and size. And I think by categorizing all that, you can maybe start to go back and see, well, where did they come from? Were they generated from some process below? Another thing I can say, and I don't think these are gravity waves, but I have clearly seen structures, differential TEC at the ocean boundary. Like when you're at the boundary of the ocean and the land surface, you can see waves propagating along that. And there's a name for that. I forget what type of wave that is, but all of these signatures are in the data. It's just pulling them out, extracting them, and then being able to work back and say what's natural, what's man-made, what's their mechanism. And there's a lot, I should say there are a lot of man-made ones. I mean, we see rockets, we see, you probably don't, but there was a huge explosion in Texas at the same time as the Boston Marathon bombing. That's why I remember it. And this explosion in Texas, they could clearly see it and the waves that were generated after in the TEC data. And that was man-made, for example. So I don't think I've answered your question other than to say there's a lot of work there and we're looking at it. And if you want a research area, I would say it's open, wide open.
Yeah, thank you so much.
Yeah, I have, yeah, okay, please, I have some
Oh,
couple of questions here. It's okay.
Please go.
So, yeah, starting with in one of your slide in incoherent scatter radar presentation, you showed that you have one antenna that can steer from Florida to North Pole, for example.
Yeah, that's our
and
model.
yeah, and the other one is a fixed antenna, right? You cannot move it.
That is correct.
Okay, so that, for example, if you steer one antenna and then you fix for example, it acting as a receiving antenna, for example. So does this low elevation affects the data quality, or
And so
because
first off,
it always have the principal beam in a fixed principal beam? Yeah.
so we always send and receive on the same antenna. Okay.
Okay.
Always. So when I was saying we switch back and forth on the zenith, we send out a pulse from the zenith and we receive it. I'm pretty sure you can't, if this MISA, which is the steerable antenna, is looking towards the north and it sends back, we're not going to see any signal because we're pointed straight up. So the way we do it is to send and receive on the same antenna. Now, in the incoherent scatter world, and I think we've even tried that with some antenna in Canada, you could clearly send up a beam, and then if you had the direction right, looking at it from another place, you could receive it. But the angles would have to be carefully worked out, right? So you don't have to send and receive on the same antenna, but at Millstone, we always do.
Okay.
And you do have to take that into account, like how's radiation scattering?
Yeah. So, and the other point is other one in the GPS, for example, you showed about this Tonga volcanic eruption.
Yep.
So do we, like, for example, do you observe any precursors in the TC change?
Oh, you would ask that. So just yesterday, so our data is being used. And I guess I can give you my own opinion. I'm very suspicious because of what we just said. There are so many unusual phenomena that just happen all the time. TIDs, for example, are caused by so many different kind of sources and being able to track them back to a precursor. But there are many scientists who believe they really have seen a signal. And one of them has a company that actually is using our data and we're helping them. But as I said, they're still trying to confirm and make these measurements. I'm still a little suspicious, but I don't want to be too hesitant because I know that, you know, you can get old and set in your ways and you can't see the potential of something that's right there. So I'm just saying I'm suspicious, but they're using our data to try and look for it. And in addition, we just learned yesterday at Lincoln Laboratory, which is part of MIT, they're even looking at a database trying to do a machine learning algorithm to try and see if they can find a precursor. And we were like, what? Don't you think you should tell us? We work at MIT. So people are definitely looking at that.
Yeah.
But I should say JPL doesn't believe it. I know that. So, and I think highly of JPL. So it's up. Again, don't close your mind because of what I'm saying. Just realize I think it's going to be pretty hard to separate natural effects from. That's going to be a hard signature to prove or disprove.
Okay. So I think yeah, Nick, yeah.
Oh, it's a fine balance between like not listening to the naysayers and then not going down a rabbit hole, right?
Yeah. So, and as I said, I, in my own history, have had too many naysayers. That's why I try to be cautious here, because, you know, at the beginning when we were doing GPS, there were a lot of naysayers. And so to everyone here, if you believe in something, I think it's worth trying to go down that path. Don't listen to the naysayers, but do it with caution.
Yeah, that's true. Yeah. So if I was alone, I can ask another question. Like you said that you are using multiple observations here. Like, for example, the observations coming from the radar has a different spatio-temporal resolution, and from the GNSS is a different,
very different.
Very different temporal resolution. So when you try to mix all the observations, then how well we can deal with the spatio-temporal variability in there? Yeah.
Well, so I think that's where we have somebody working with us called Urcha who's working with doing a tomography algorithm where he's taking data from all of our GPS, also from all of the satellites he can get hold of, and the Millstone ISR. And with his tomography algorithm and all of that data, he's been able to do a three-dimensional analysis of the storm enhanced density effect over Millstone. So we've only done it in a local area where we have a lot of one advantage of where I am is there are a lot of GPS receivers there, right? In addition to this other data. We're now taking his algorithm, and other people have done this too, and we're moving it to Alaska, because now and I didn't really mention it, I have a bunch of receivers here that do scintillation measurements as well. That's why that's in our database. We're looking at that. And we're trying to come up with better tomography algorithms for this area. So that is an area of research. And I can't answer, again, I say the more data you have, the better off you're going to be. And we don't have enough. Well, I don't think we have enough data yet, at least here in Alaska. I think we need more data, but we are trying to combine data from, which I didn't show you. We use the Superdarn convection patterns, which is another radar that gives you information about what's happening over the polar cap and sort of the direction of the flow, the plasma flow. And we actually overlay our TEC data onto that. We are working with Ampere data, which gives you some sense of the magnetic field and everything. We're working with a lot of the all sky cameras here and using different filters to look at the intensities and see if from the intensity, can you get information about the TEC? There are a lot of different ways we can start to combine data, but the big problem is how to do it the best way and what information can you get from the different sensors. And that's the future. That's the future for all of you, is trying to try and get us to come up with formats that are easy to use and easy to combine data with. So,
okay. Yeah, thank you.
Angelo, you want to just unmute yourself and ask your question out loud? And if anybody else has a question, with we're last call on questions for Anthea.
Okay, yes. Hello, thank you for the two presentations. They were really nice and rich. My question was about the antennas and the instruments that you use. What are the restrictions in using instruments of that size? Like, what are the difficulties?
you mean using the Millstone Hill radar?
Yes.
Okay, so you have to get a lot of, even for smaller instruments, at least within the USA, you have to be granted a license to radiate and at certain frequencies. So you have to go through a lot of official channels to get those permissions. It's not, that process in and of itself can take years or a year. I mean, it can take a long time. We've had an established, I work at a large radar site, as you can see. We've had a long history of having this license, but that's a big process. And then, of course, funding for all ground-based measurements in the US is difficult. We're trying to get right now, every instrument I showed you is paid for by the National Science Foundation. And one of the problems is the National Science Foundation is a science-oriented organization. And so the stability of long-term funding for major instrumentation is not part of their budget. I mean, if you look at it, we're not like NOAA, which funds a bunch of different instruments that they need, or satellites. Where the ground-based instruments have always been thrown in with NSF, and NSF is a science organization. They don't really do operational maintenance, if that makes sense. And so there's a funding gap, I would say, and it's across the board. It's not just for GPS. It's not just for incoherent scatters. The National Solar Observatory has the same problem. All the magnetometer networks have the same problem. Pretty much every single ground-based instrument sensor network has the problem of stable funding and operational maintenance and communication. So I don't know if that answered it, but those are all issues that we deal with on an ongoing basis.
Okay, thank you. And just a follow-up question on that, like, how do you decide on the site that you will build an instrument like that? What are the environmental, or like, I don't know, what are the restrictions there are?
Funny you should ask. So, I mean, I think now we're actually thinking of proposing, there's something called the National Decadal Survey, but we've proposed to build a new mid-latitude radar because, for example, we just lost Arecibo, that's gone. The Millstone Incoherent Scatter Radar is over 50 years old and its lifetime is somewhat limited. To build one of these instruments can take as long as 20 years. I mean, when they started the plans for the Poker Flat radar, which was the last radar the US built, it was in the works for over 20 years. So if we're thinking in those terms, now is the time to start planning where we're going to put one. And the group that I'm with right now wants to put one somewhere affiliated either with the University of Michigan or the University of Illinois. And we're thinking in the middle of the country towards high up to sort of look at the processes that are coming in from over Canada, so that are high mid-latitudes, but also getting some of the polar, the rural region coming over. That's what we're thinking of, but you're right. How do you figure out where you can build it? What kind of radar are you going to build? Who's going to not, what farmer in Illinois is going to not complain about having these 50 megahertz radars? These are all huge plans, and it's something that you have to start working on now because it's going to be a long process, easily 10 years, and that's at best. So we're starting to look at that. And I think other people, even here, the Pfizer radar that I showed you, which I think is a fantastic radar, it needs major maintenance in the next 5 years. It's already 20 years old, and we need somebody to invest in it, to keep it. Now that's already licensed, I mean, it's part of the Poker Flat rocket range. They have the licenses to transmit, and they're not gonna, but we need funding to keep it going.
I see. Okay, and one more if I have time. I had heard that.
Omina had a question, and then I think we're gonna call it.
Okay. So should I ask? No, there's no.
I want to get Omina's question in first.
Okay, cool.
Okay,
thank you very much again.
Yeah, in the presentation,
we can barely hear you, Omina.
I said in the ISR radar,
better.
Yep.
You mentioned that the hours for the milestone radar system does not operate throughout the day in your research lab, that you use it for, you mentioned a particular number of hours in which you use it, but
so that's
the duration of
the I
so
mentioned hours. Yeah, okay, go ahead.
So my question is, if the radar is not available throughout the hours of the period, how do you not determine when you study these ionospheric variabilities that occur in the ionosphere?
So, well, there's two ways we do that. One, the reason we only operate for $1,000 a year is, or 1,000 hours a year, is because that's all we have funds for. That comes down from National Science Foundation. We actually would love to do it full time, but we just don't have the money. And we have to, it's actually even people, we have to have operators there. We can't run the radar without an operator on site. So that's our limitation. So to study variability in our plan, we typically try to have some what we call long runs, where we run straight for 30 days or so. We typically try to do that once every year or once every other year, but those are we try to do these long runs at different seasons so we can try and get the variability. But yes, this is a problem. And the other thing we try to do is if there is a geomagnetic storm that we can see coming, we'll look at the NOAA forecast, we'll turn it on and try and track, because we usually have some warning that it may be of interest. But again, that depends on what's happening at the radar and whether we can get everything set up to run. But the reason we're not running 24 hours a day is that we do not have the funds to do it. So.
Thank you.
Okay, great. Let's thank Anthea for both a great talk and a great discussion afterwards, and thank you for coming back. And now you get to go deal with the other participants in your other summer school, right? Yes.
Again, I want to remind everybody, please consider looking or applying for the ISR school next year, because we have them every year. That's number one. And number two, if you do have questions, they have my email, or I think you can even look up my name and you can find it at Haystack. But email us and we'll give you information about Madrigal, because I did cover stuff pretty fast. And but especially if you want to access our data, we'd be more than happy to help you or put you in contact with people who can help you if I can't. Okay.
Okay. All right. Thank you, Anthea.